Welcome back, students. Today we're going to do some graph coloring. Now, don't think that you are in art class right now because we still are in Finite. Because while we are going to be coloring, and had I been there, I probably would have given you colored pencils, we are not actually going to color in the way that you think because we are going to be using a very specific algorithm. So take a look at a map, and whenever you see a map, usually you're going to see different sections of that map that are colored differently. Now, it's not that we use all different colors, it's the fact that any section that's next to another section, or let's be a little more mathematical there, any section that is adjacent to another section will not use the same color. So let's look at Indiana. Indiana is obviously adjacent to Ohio, and notice that Indiana and Ohio are using different colors. Indiana is adjacent to Kentucky, and Indiana and Kentucky are different colors, and so on. So we're going to be doing the same thing with our own maps. So here's your first map to take a look at, and I want you to pause this video, and I want you to think about how many colors would it take to color this map. Now, the only rule is that two sections that are adjacent, which means that they share a common edge, cannot have the same color, but any section that shares just a corner, okay, they are allowed to have the same color. All right, so up here in the map of the US at the four corners, Utah and New Mexico could have had the same color. Okay, same with Colorado and Arizona. Now, while they don't, they could have. Okay, so that's your rule. So come back down here, pause the video, and think about how many colors would this take. So what you're going to do is you're going to take a map and you're going to turn it into a graph. So each of the sections on the map is going to translate to a vertex for the graph. So we have A, B, C, D, and E. So that means I have 5 vertices. Now you can put these vertices wherever you want. However, I suggest that you place them pretty much in the same location where they were in the map. All right, so we have A, B, C, D, and E. And then these edges that connect specific vertices are saying these vertices are adjacent. So D and A shared a common edge, so D and A share an edge in this graph as well. So two mathematicians, Welsh and Powell, came up with what's called the Welsh-Powell algorithm in order to color any map. And so what they said is you need to look at the degree of each vertex and start off with a vertex that is of most degree. So degree 1, 2, 3, 4 for vertex D, degree 3 for vertex E, degree 3 for C, 1, 2, 3, 4 for B, and 2 for A. So we have a tie. We have 4 and 4. Pick one. It doesn't matter which one. The way you color your graph might not be unique, but figuring out what's the least number of colors to color it is going to be the same for everybody. All right, so D had the most, same with B, so I'm going to start off with D. I'm going to color it red. And then what I'm going to do is I'm going to then color any vertex that's not adjacent to D also in red. But upon further examination, it looks like every one of these vertices is adjacent to D, so that means I need to pick a new color. And by the way, if you don't have colored pencils, you can just use numbers. I could say this is number 1, my first color, and then use a second color, and so on. All right, so D and B both had degree 4. I already colored D, so now I'm going to color B with pink. B is adjacent to A, B is adjacent to E, B is adjacent to C, so none of those can receive the color pink. Now I'm going to go on. C and E both have degree 3, so I'm going to pick one, doesn't matter which one. I'll do C. C is adjacent to E, but A is not adjacent to C, so now we finally can use the same color again. So A and C can both be colored the same, and then E would need its own color. All right, so we have red, we have blue, we have pink, we have green, which means that the minimum number of colors is 4. That's going to be what's called the chromatic number. Chromatic number. Okay, the minimum number of colors needed is the chromatic number. I will spell that here in just a second. All right, chromatic number. Okay, right there it is. So the chromatic number for this map, for this graph, was 4. Let's do another one. All right, so here's a new map. Okay, pause the video, try to do this on your own, and see what the chromatic number is going to be. All right, so here's what my graph looks like. Okay, again, it doesn't have to look identical to this. I suggest that you try to keep the vertices in the same location, but again, that doesn't have to be the case. So it looks like E is the one with the most degrees. So E is going to have the most conflict. So I start off with it. I'm going to color it red. E is not adjacent to this one, A. E is also not adjacent to this, not adjacent to this, and these weren't adjacent to each other, nor were these. So that means that all of these vertices can be colored the same. So then I'll need another color for the rest. And this one, this graph, has a chromatic number of 2. All right, so here's another example. Here's another graph. Please pause the video and try to figure out its chromatic number. All right, so here's what my graph looks like. A has the most conflict, so I'm going to color A first with the first color. It's adjacent to everything, so now I need to pick a second color. I'll go to B, and B and D are non-adjacent, but now I need a third color, and I'll do E. E and C are non-adjacent, which means that this graph has a chromatic number of 3. Let's make it a little bit harder. Let's have some more sections. Okay, please pause the video and try to find the chromatic number of this graph. Okay, here's what my graph looks like. Vertex A has the most conflict, so I'll start by coloring it. The only vertex it's not adjacent to is B, so I'll color B the same color. Now I'll switch colors. It looks like all 3 of these vertices have degree 4, so it doesn't matter which one I choose. Graph colorings won't necessarily be unique, but again, the chromatic number will always be the same for a particular graph. All right, so I'm going to color that one pink. Can't color anyone that it's adjacent to pink, but this one could be pink. But now because I colored this one pink, this one can't be. But this one could be. But now this one can't. And this one couldn't before. All right, so now I need another color. And I'm going to go to another one of highest degree. So now this one can't be blue, but this one could be. And this one could be blue as well. And then one more color, it looks like, because I have one more vertex. So red, blue, pink, and green. That means this chromatic number was 4. All right, now we could keep going and do several more examples, but there are mathematicians that have already figured out graph theory. Okay, they've already come to some conclusions. And one conclusion that they came up with is what's called the 4-color theorem. So you can scroll back, go through this video again, and you can see that the chromatic numbers that we used were always 4 or less, and that will always be the case. All right, any map, this is what the 4-color theorem says. Any map that can be drawn on the surface of a sphere could be colored with at most 4 colors. All right, so you're probably thinking, I'm not going to use this. Okay, well, right now I am, because this is real life. So I'm using it right now in real life, but where could this really pertain after finite math? Okay, am I going to use it again? You actually could. All right, and here is a scenario where it could occur again. A school has 6 clubs, and the following students are officers in those clubs. Each club would like to have a meeting every couple of weeks, but because of the shared officers, it is necessary to arrange the meeting days so that no students are scheduled for more than one meeting on the same day. What is the minimum number of days needed? All right, so this one isn't a map. Instead, it's a table, but we could still turn this table into a graph. So what we're going to do is we're going to put down what all of the clubs are. And then once again, edges represent conflict. Okay, so what I'm going to do is I'm going to draw an edge between any clubs that can't meet on the same day because they have a shared officer. So it looks like Alex is a part of student council, chess club, and key club. So I'm going to draw an edge from student council to chess club. I'm going to draw an edge from student council to key club. But then I'm also going to draw an edge from key club to chess club. All right, so those would be conflicts involving Alex. For Barb, she's a part of student council. She's a part of SAD, and she's a part of cheer block. All right, so for Barb, I'm going to have to draw a conflict between student council and SAD, student council and cheer block, and then SAD and cheer block. And then for Cole, he is an officer of key club. Sorry, no, that's chess club. Chess club and Spanish club. So chess and Spanish now have a conflict. Donna is student council as well as key club. All right, so that conflict was already taken care of by Alex. And then Evan has conflict between student council and cheer block. So student council and cheer block, that conflict was already taken care of by Barb. All right, so now I'm just going to use that Welsh Pal algorithm, and I'm going to color. I'm going to start off with the club that has the most conflicts, which looks like Student Council. I'm going to color it pink, okay, which represents a day. So whatever day it's going to be, it gets its own day. All of these clubs could not meet because they would have conflict, but Spanish Club has no conflict with Student Council. So now I'm going to pick another color, which represents another day. And it looks like Chess Club's the next vertex of highest degree. Chess has conflicts with Key, Student Council, and Spanish, so it could meet the same time as Cheer Block or SAD. Okay, so it doesn't matter which one, but once I choose one of them to color, I can't choose the other one because SAD and Cheers Block have a conflict. All right, so now I'm going to pick one more color. And SAD, I'm going to color it green, and it doesn't have a conflict with Key Club, so I'm going to also color it green. All right, so this is not unique. Okay, it doesn't mean that these are the date, like chess and cheer block doesn't mean that they have to meet at the same time. Okay, but this is how one possible scenario could be, and it means that the minimum number of days needed would be 3. All right, and that is your lesson over graph coloring. Thanks for watching.